I don't know if that helps.
You can zoom in.
Yeah, I guess I can, but then I won't be able to show.
You can grab it. There's a grab tool next to the selection tool.
Yeah. Well, right. So basically, this is mostly Adam's work. So if you have any more questions, I would encourage you to write him an email and ask him for information. Well, I'm from David. I'm from the University of St. Andrews, and there we like to make it easier to write parallel programs. Parallel programs that have some nice speedups. So there is this nice shiny tool, the Scale library, which is basically a library of algorithmic skeletons. So if you don't know what algorithmic skeletons are, they are basically implementations of common patterns of parallelism. So generally they were introduced by Murray Cole in the 80s, well, since we have a functional language and we have higher order functions, we can have implementations of these algorithmic skeletons. And in Scale, actually, you have some representation of the structure of your program, something that looks like the AST or some parallel program, and then a Scale run function that takes this structure and runs it. And using right, I don't know if it's in there or not. In the run, so basically we have used a refactoring tool to introduce automatically these parallel structures to Erlang programs. And so we were running our examples, we introduced some nice parallel structure to a problem that was supposed to give us some speedups. We got actually some slowdowns. And the reason is that the parallel pattern, the communication pattern between the different workers of the program required to send data types that needed to be copied. So that copy was taking lots of overhead, and finally, basically, it ended up being worse than just running the sequential version. So we basically started changing the data types for something that doesn't get copied, such as binaries or ETS tables. And we thought, well, maybe a good idea to do that automatically. So basically, that's where this refactoring transformation was introduced. So basically, it allows you to pick some function that uses some variable from some data type. And so if that, as it takes that variable as an argument, and you select the variable and you ask, okay, I want to change this to be a binary or an ETS table or something like that. And it recurses, so basically the refactoring transformation recursively enters into the function, makes a copy, and recursively traverses all the user-defined functions and substituting all the affected parts of the code by the new, converts them to the new, to your target data type, basically. With some exceptions, where you need to actually revert the transformation and get back to the original type, but some of them are limitations of the current approach, and some of them are things that we need to do. So, for example, well, in here, so that's the idea of how this works. So if this is a function and x is the argument and it's your list and you want to convert it, you apply the converter, which is basically one of the transformations, and the idea is to generate like this island of functionality that is altered by the transformation. And then each time you need to either send a message to some other node in your program or return a result or something like that. you do a revert and make the conversion back. So that may have some overhead, but hopefully if you choose a computationally expensive part of your program, you will be able to take advantage of that and parallelize it a bit better. So we tried this with this approach with a bunch of examples. One is the image merge example, which is basically takes a stream of input images and does some calculation to them and merges them into a single one. The embody, the Barnes hat simulation, and the matrix multiplication. So generally, if you're going to run your program on a multicore, it's a good idea to use either ETS tables or binaries, as you see there. But for the Barnes hat simulation, it was actually roughly the same, and the reason we still don't have any convincing idea of why that was happening, but the idea is that the messages that were sent between the different workers of the parallel program were small enough, and what we were doing was actually mapping some computation over all of them, so over all the data that we needed to do the computation, and then fold them. So that was not that computation was well. So yeah, and yeah, this is the diagram that explains roughly how the approach works. So which is what I already explained a while ago. So it's basically selecting some variable, and then we extract the code and apply several different transformations depending on the case, on the expressions that you find in your function. And yeah, I could walk you through this example, except that. Okay. Yeah, so this is the example of how we apply this to the image merge example. I'm only explaining a few of the steps, but basically, if we select both x's and y's here, the idea is that the function body is lifted into this f, and here what we are calling is f with converted x's and converted y's. So one of the very first things that we need to do, since we are converting it to an ETS table, is to add to copy it, because we are going to be making transformations to it, and we still don't know whether we are going to need the original one. So ETS tables are mutable, so that's something that our transformation needs to handle. And then it's basically a matter of walking through these functions. If you have a map over lists, then we convert it a map over the things that are in the ETS table, and in case we find some user-defined function, we would jump to this function and keep doing the transformation. And there is a number of limitations to the current the current refactoring transformation. Like, for example, we don't support nested, so the transformation to act on nested. So if we have a list of lists and we want to transform the list, and it's stored in this larger data type, we don't go into that. We would just revert the transformation, because it would be very complicated. And well, we're working now on these limitations. Actually, Adam is probably right now working on those limitations, and some of them may be solved by the time we finish. That's a general overview. I don't know if you have questions or want to take a closer look at the poster. I'm happy to show you that. Yes?
So I'm a bit puzzled. So if you have a parallel program operating on a list, and you remember that one's in part to its subprocesses, then you're copying the list from the heap of one process to the heap of the small process. So if you convert it to a binary, then you copy the list into the binary storage area and then just pass pointers. But if, in order to use them, you have to convert them back to lists in the processes that actually do that job, then you've got to copy it out of the binary storage area and back onto the process heap. So how can it be faster?
Right.
So I want to add to that. The same thing happens with edge. I mean, with edge, you copy stuff in and out. There's no pointer to the edge table. If you have a public or even a protected table, there is copying in to put the stuff into the edge table and to actually get it back. So,
Right.
so
But the-
to add
the
to
one- yes.
John's question, it's not like you are avoiding this copy. So something else is happening.
So I think in your the way you formulated the question, I understood that. Correct me if I'm wrong. That the fact that you have to revert when you send some message to some other part of the application, that means that you're going to end up copying things anyway.
Yes.
Yes, but the point is that we are introducing the parallel structure inside this island of modified functionality, which means that we are not going to do any revert inside there. So once we finish, so this transformation is done before we apply we introduce the calls to the scale library in the parallel structure. So we don't actually need to convert back to list, and that means that we don't actually need to end up copying things. And I don't know if that answers your question. Because when you copy something, well, I mean,
Let's start with something basic.
yes.
So what are your processes here? I mean, you do a parallelization of something. You have to start with some processes.
Yes.
So what are the arguments to these processes?
Right. So yeah. So you mean that if we have some parallel program, the arguments would be the lists, for example, the list that you are operating over, or the data type that has the data over which you are going to do the parallel computation. Is that what you are asking?
This application has what data and what is shared between the processes that you
So in the image merge example, for example, you would share the whole images. You would be writing a new image out in the parallel process. In the matrix multiplication, you would share the chunks of the matrices in the different processes.
What does it mean in Erlang to write an image in different parts? There is no, there is no mutable data structure. You cannot say, okay, I'll write here a process and the other one will write there. It's not like, you have a big array and you split this array into parts and everybody is writing into a different part. There is nothing like that in Erlang.
Sorry.
Yeah. So maybe I have a question I'll clarify. So you're using scale
Yes.
for algorithm skeletons, right?
Yes.
Are you using the scale are you using scale implementation in Erlang, or are you using scale implementation bindings to scale from Erlang?
So we are using the scale library implemented in Erlang.
Okay. So this code you shown on the right,
Yes.
it's sort of list map is calling something within scale. Sort of
No, that is just the Erlang code. I mean, we are not showing the resulting parallel program here.
Yeah.
We are just using the data type
but
transformation.
the code on the next bit uses ETS list map.
Yeah. Yes.
So you don't need to go back to list to perform operation.
No. That's so the transformation is applied to all the user-defined function that you want to convert. So you are right. So you need when you need, for example, for the result of this function here.
Yep.
So inside here, you are working with ETS tables as if the function was originally defined to work with ETS tables.
So is that where the speed up is
Yes.
coming from?
Yes.
So can you show us some code that gets parallelized? Because this is not, sorry to say, this is nothing. There is no code that gets
Yes.
parallelized. There is
So-
no
so-
stone. There is nothing here.
Yes, mainly because in this poster I was presenting the transformation for changing from one type to the other. I can ask Adam for the code and I can show it to you if you're interested. But
Okay,
Okay.
let me,
Sorry. Sorry.
could you let me to explain? So I think that, so it's two different stages. The first one is just, I think, a simple sequential refactoring from sequential code to another sequential code. So you used lists before, and then in the same code you are using ETS tables, just a storage. So instead of a list, you are using an ETS table or a binary, but it's still a sequential code. So this refactoring, I guess, is just the transforming one sequential code to fragment to another sequential code fragment. And then later, on that code, you can introduce scale, and if you introduce scale, then you may get a speed up on a code that's using binary or EPS or I don't know what kind of data set. So it's two different steps, and I think this code is just a sequential code.
Exactly.
So it's not a parallel code. So that's why it's a bit confusing, because the speed ups related to the scaled version of the code and not for this code,
Yes.
I guess. So I think that's the
Thank you very
Point
much for
of
the,
view.
for the clarification.
Okay.
Yeah. Yes,
okay,
but that's
so
the
speed ups
idea.
is not for this transformation. It's just an initial step. So let's assume that you have a list, so some function that operates on list. And
Okay.
when you want to use scale to parallelize that code, then you may not get the speed up because of list, and there is a huge copying in the memory when you are using list. Even when you parallelize the code, you can get a speed up. But if you do some reshaping of your code, your sequential code, and then you introduce scale on the refactored version of the code, then you may get a speed up. Okay, I'm not quite sure.
That's exactly
So,
How
so,
this
so
happens,
I
but-
still don't understand anything. So you have, let's take an example. You have a list and you want to sort it. And now you want to do a parallel sort. What would you do?
So I would have to understand the problem in detail, I would say, but
I think it's a simple problem. You can parallelize it with quick sort or something.
no,
like that.
but that's the idea. So for if you have a list, I would
So
have
you
to
take
see
the list
what
and you
list-
put it where? You would make the list into a binary?
If it's worth for parallelizing, yes, that's the idea is that this is a refactoring transformation. We are not doing this automatically. We are not converting all the lists to binaries or to ETS tables. So
But this is trivial. I mean, you can just have list to binary and binary to list. So this conversion is really nothing. The question is, okay, so you have converted it.
I would say that it's not that trivial. I mean,
It's
you're
very
converting
trivial to
two
convert
ETS
one to the
tables.
other. The problem is, okay, now you have the binary.
Yeah.
How do you sort this? This is not a mutable data structure. You cannot just, change bytes there.
Right, but you can still generate a new binary with the sorted data. I mean, I don't really understand what's the problem, to be honest.
Are lists in Erlang mutable?
Huh?
Are lists in Erlang mutable?
No.
So how would you sort a list?
You would have to partition it and give the partitions to different processes.
But doesn't that mean that you could do the same with ETS list?
I don't know what ETS list is, so I cannot answer this question, but I know what binaries are. Binaries is a big blob of bit stream.
Okay.
So if you have a big binary, you could divide it into two halves without copying it. And you could do that repeatedly. And then you could send sub-binaries that would just be pointers to a variety of processes.
Exactly.
But when you sort them, if you create new sorted binaries and send those back again,
You have to be copied, you know.
or maybe you'd end up with a fragmented binary as a result. You might be able to do that in that couple of years. But if you implement quick sort and you want to partition a binary, then you're going to have to copy it.
Yes, and this binary will come to a point where they're not going to be shared anyway. So there are a lot of things that I don't understand, you know, and it's interesting. Exactly, that's why all these questions are being asked, because it is interesting, but it's very opaque, I think, at this point, at least to me.
So I'm not an Erlang person, but I just want to ask one thing.
Yes.
So is list in Erlang represented as a console?
Yes.
Yes.
So there is a really common problem in Haskell that there are multiple representations for string, because passing around a string which is a list of characters is extremely inefficient. So quite often you do exactly this operation. You translate it to text, which is just a flat sequence of bytes with a length, and you move it around. And then once you want to use it as a list again, you perform translation back. So maybe the same approach applies, that instead of having the overhead of boxing and pointers, you just have one flat data structure with length and you pass it around.
So Erlang strings are not represented quite as bulkily as Haskell ones are. Nevertheless, there can be an advantage in converting into binaries.
Okay.
So I suppose conceivably it might be cheaper to copy a binary than to copy a string. But what does this diagram show? So this shows a speed up of 0. that means on 8 nodes it didn't run at all.
I'm not sure if this is 0 or... Yes, well, it's...
Okay.
No, that's... yes, that's...
So after it goes, it's so much overhead
But
that it's even worse.
yeah, there's a really big overhead on copying all the lists once you start adding workers. I mean, to the parallel program, but it got under 1 definitely. I mean, I'm not sure exactly how bad it was. Probably not exactly 0.
What is the baseline here? I mean, yeah. So speed up to what? It should be the
Against the sequential list version of the program.
Oh, and it uses this.
Yes.
So I may be in the minority of people who've used Skell, the library that is underlying the parallel implementation. So I confess a lot of skepticism that you're expressing also, but the code that's in the right-hand side is only the sequential part. So it's my guess that for the parts from, say, line 2 through 5, that first map, that in the parallel version is one Skell stage in a pipeline.
Yes.
Yeah.
That's
And so it might also make a difference whether it is a singular pipeline versus the Skell pattern for the worker farm, where the single input stream is farmed out to multiple worker processes. So if that's true, then the calculation of the y's and the white are, and the result are actually being performed in different stages. It would be really helpful to know what that structure is in the Skell description of the communication pattern. I don't know if that's available, but that could answer several questions.
Yes. I can try to get it and show it later if you want.
We're putting you on the spot, I understand. So
Yes.
Right, so is it pipeline or is it a farm?
So it was a pipeline. I think it was divided in 2 stages, and there was one stage that used the farm, a task farm. Yes.
But when you use this stage to change the sequential version, does that affect the skeleton that is selected afterwards when you translate, when you do the parallelization?
Well, I'm assuming that yes, well, the structure will be different if with one data structure and with other data structure. Mainly because there will be more cost in some operations that later you will have. But those speedups are all using the same parallel structure and increasing the workers of the task farm. It's, yeah, so in the pipeline, the most costly part is the last one, and that is put in one stage of the pipeline where we are a task farm. We increase the number of workers, and that is the speed up stuff that we get with the.
Did my question help you out at all?
No, the thing I'm very much missing here is where are the spawns?
No, but this is that's what was explaining a while ago. So what I'm showing here is not the way we parallelize the program. So there are so there are a number of papers that they published about using scale for parallelizing programs that get you some reasonable speedups. So this is an improvement, something that you would do before introducing this scale library. So what I'm showing here is the sequential part of the code, so how this transformation works. And preliminary results that show that it may be good doing in some cases.
So what is an X list? It's a table, but what are the keys?
Sorry, where?
So
Down.
after transformation, then let's go to using an X list.
Yes, so that's a library for replicating the same behavior with ETS tables that we get from lists. So it's like implementing an abstract data type for lists on top of ETS tables, so that we can do this transformation.
And so what is the representation? How is a list represented as an X table?
So I apologize, I can't remember right now the details of the implementation of the ETS table. I can look at that.
Is the same ETS table is used by the concurrent processing?
By the sorry.
So is the same ETS table is used by all the concurrent processes that you will introduce later?
Yes.
So I guess maybe a list is represented by an X table in which the positions of the element is the key.
I'm guessing that, yes, but I can't remember right now the specific details. That was my first guess.
So then XList's map is presumably copying elements from an input X table into an output X table and applying the function.
No, it's that's why we copy the original ETS table. So.
The original ETS table, that doesn't make sense. What is the original ETS table?
Well,
It
the one
doesn't
that we
exist.
received at the beginning, so as an argument to the function. So we receive an ETS table as an argument of the function, which is this one that comes from the conversion there. And we have to copy it, mainly because we are going to be updating it in place. And the refactoring transformation knows at which point you have to do the copy so that it's safe to do the in-place transformations.
So then maybe XList map is spawning a number of processes, each of which takes a range of elements back to the function.
So this ETS list map, called map, that is right. So the one that I'm showing here is the sequential version of it. So it basically traverses the elements and applies the function. And it's later when we are going to replace this ETS list from map by something else, by the skeleton, by the corresponding parallel proof.
I really don't understand why you copy the X's state.
Well, here you wouldn't need to, but unfortunately, since we are modifying it and our tool isn't able to detect that actually, that we are not going to be using it. But here we are returning the length of this ETS.
But okay, so X's map is modifying X's, but not changing its length. Sure.
That's right. That's why I'm saying that it's a limitation of the tool. So we should be we don't know that this is computing length in the tool, and we don't know what is this what is going to be placed in here. So since we are modifying X's, the original one, in here, and we are returning the length of this of the original list, so we need to keep the original copy. But you are absolutely right. So we could be detecting some cases in which basically it's not needed, like here, for example. And that's I think that we could be doing this.
If you don't mind, I just want to show you a very short example. I found an example in a previous workshop paper about scale, so maybe it helps you. Just because it's also the image merging example. So here we had there were 3 different maps. The first was remove alpha, then the second one. So there were 3 lists map call. Each of them can be F3, F2, and F1. So representing by the F function. And here, so it's an extra step after to introduce the parallelization using the scale do function. And this phones and message sending and receiving is inside the scale library. So it's implemented inside the scale library. So this is just a sequential code what David is presenting. So you have to do an extra. Maybe it's not the same version of that code, but image merging example. But it should look like this when it's parallelized. Maybe there is. I haven't checked. So this is the merge. It's a 2-staged pipeline. So maybe that was that you've explained. Yes. There is a pipeline and each stage is a farm or something like that. Yes. So a list map call is replaced with a farm skeleton. Okay? And I think the speed ups related to that calls and not the sequential.
No, yes, that's absolutely right. So it relates to this code when applied to the different versions, the one that uses lists and the one that uses ETS tables and binary.
So in the actual processes that are created, and this diagram doesn't show them, in the skeleton. So there is the process that's calling skel_do. That's sort of the parent process, and then it will create a pipe process. So now we've got two, and then there may or may not be an intermediate process for the farm that has one process that is sort of the taking input from the pipeline, and then the worker processes, and then a collector at the bottom. So then the message passing, or the processes in the message passing is either an additional 2 messages or 3, I'm not quite sure. And then we have another farm that would again be adding another 2 or 3 message copies. And then the Skel has a final process that is collecting the final results at the end and then sending them back to the do Skel caller. So the way Skel works, my understanding is that, what was the number that I just tallied there? It's probably at least 7 messages that would be passed. So this is just speculation, but given what I know of Skel, the message passing overhead for things like the processes that aren't doing useful computation work, the farm process at the top and at the bottom, taking the input and collecting the output to send to the next stage, they're not doing real work from the actual parallel application point of view, but they do have the overhead of the message passing, and so that can be where the overhead from the list copy comes from. And so that dead weight of those processes just doing the message copying is a likely source for at least some of the speedups shown there.
So you're saying that some of the messages would be copied several times between several different processes in order to get from where they begin to where they happen to be processed?
Yes.
So maybe an alternative would just be to optimize the message passing in the Skel library so that things get sent directly.
Yes. But the Skel library, for example, has no fault tolerance. If anything, any stage, any farm worker, for example, throws an exception or otherwise crashes, it will destroy the entire farm and the do Skel caller, and life is chaos. And so, and maybe that's the kind of death that you want, in the sort of Erlang style. Let them all crash. While I was at Basho, I was trying to use Skel for a different purpose, and I really needed fault tolerance, and I basically had to throw out most of the code because this was basically a research prototype, and as a practitioner, I couldn't handle that kill everything, failure semantics. So there is a lot of work that could be done on Skel to implement the pattern you just described. I certainly agree.
Okay. We need some time to have a tea or a coffee, so let's close this discussion now, and you can continue offline. Okay? Thank you.
Okay.